All right, ready for the shortcut? In your unit conversions part of your data booklet, you got 1 rad equals 180 over pi. Really useful. A lot of useful things in here. This one is often overlooked, and that's your Hc equals joules times a meter and the electron volt times a meter. So, with our last problem, we did E equals Hc over lambda. The Hc is given to us. We had to find E in terms of joules and in electron volts. So we could just say, okay, there's my numerator for my joules, and then divide by my 0.1. So take this and plug it in here. And then for the electron volts, I can just do the same exact equation, E equals Hc over lambda. 0.1 on the bottom, my electron volts, plug that into my numerator right there, hit the divide button, and then be on my way. Hopefully that helps you. All right, a little bit of review. Electrons in an atom exist only at discrete energy levels. These are your energy levels. When an electron jumps shells, it's going to come up here. Let's say, maybe. So if this electron becomes excited and it's going to jump up, that would mean some energy had to come in, right? So usually electrical current is going to come in, ionize this electron, and it's going to absorb the energy. Here we go. Absorb the energy. And then when it does that, it's going to drop back down, perhaps all the way down to 1, or maybe it's just going to first drop down to 4. Each time that whenever it does drop down energy levels, it's going to emit a photon. Poop out that photon. Okay, so this is the emitted energy right here. And what this will produce is the emission spectra, because the energy is coming up, the electron is ionized, and then it's going to drop back down energy levels and emit out a photon, creating the emission spectrum. A photon is emitted whenever an electron transitions from one energy level down. How many different transitions are possible between these 4 energy levels? Here we go. I warned you about this, right? So in between these 4. Well, the first thing I'm going to do is I'm going to take the big one. I'm going to go, okay, we're going to start at E4, between these E4. So E4, and it's going to go all the way down. And then it might go here to here, and then here to here. That takes care of 3. Is that all that it can do? No. Because what about these other, if we started out at 3, then we go 3 to 1, and then 3 to 2. Well, what if we started out at E equals 2? Then we have this one. Okay? So that would be 6. 6 is your answer. Review on the Bohr model. 0 electron volts, negative 13 electron volts. So this is a hydrogen atom. All of this stuff up here, all of this is going to be the excited state. These are your excited states, and this is your ground state right here. I would make note of that. Ground state, n equals 1. Excited states are up here. Different energy transitions result in different energies or wavelengths of light that are absorbed or emitted. Remember, if it goes all the way down to the 1, all the way back down to ground state, it's a Lyman series. If we're going to the second energy level, then it's a Balmer series. That's our visible light. And then the Paschen series, the infrared. What is the wavelength emitted? Try it out for yourself. I'll be back with a solution. We're given the equation here. What we don't have is E. Well, we're given to it here. That's the whole point of this diagram. So the E, remember, this is really a delta E. This is really the change in energy. So our change in energy is 1.15 0.5 minus the 13.6. And when we do that, the change in energy is 12.09. What are the units? Electron volts, electron volts. That is our change in energy. Okay? HC, oh, given to us. Which one do we use? Which one do we use? Joule per meter, joule times meter, joule times second. That's a typo. That's not joule times second. Sorry, my brain was disappeared and then it's back. This is an electron volt times a meter. Wrong unit. Sorry, typo. So, which one are we using? Is it the joule times meter or the electron volt times meter? Good, it's the electron volt times meter. So it's going to be 1.24 times 10 to the negative 6 divided by 12.09, because that, and then this equals this, right? Plugging that in our calculator, we get 1.03 times 10 to the negative 7 meters. Now you can change this and put it into 1.03 times 10 to the negative 9, which is a nanometer, if you'd prefer. Either one of those will be correct. Just mind your sig figs, of course. All right. Try this one. It's all yours. I'll be back. Right, so we're talking energies and we're talking light. So this is going to be E equals HF situation. E equals HF. What's that other version? Oh yes. Lambda equals HC over E. Same equation, E equals HF. This is given to us here. Here. Again, typo, that's a electron volt times a meter right there, don't be fooled. Let's get on with the solution. Stop babbling. All right. First thing I'm going to look for is this E. That's what my diagram is providing me. It's my change in energy. So my change in energy is going to be this negative 0.85 minus negative 3.4. Minusing a negative is adding a positive. So we get 2.55 electron volts. Is going to be our change in energy. Lambda equals HC. HC, we're dealing with electron volts here for the energy, so which version? Right, it's this, it's not this, it's this, this, this. Okay, so we get 1.24 times 10 to the negative 6 divided by my E, which was 2.55. Just make sure your energy is either in joules or electron volts. And if it's in electron volts, then we're going to use this number. If it's in joules, then we're going to use this number. I ended up with 2.86 electron volts. Is that right? Did I mess up? Just kidding.